Okay, our next topic is electrostatic potential energy. And potential energy is related to the amount of work that's done moving a charged particle around an electric field. So we imagine two charges and little q starting here at rest and ending up a long, long way away. Now, as we move that charged particle, we note that the electrostatic force will change. Now, if these were, say, opposite charges, then the electrostatic force would be attractive and would be relatively large here, and it's going to get a lot smaller way out here as you get further away. So because the force isn't constant, we can't find the work using the product of force and displacement, and instead we have to consider the change in force over distance and find the area under this graph, but it's a curve because it's an inverse variation. And so we have to integrate that using calculus, which we haven't covered yet in our math courses. So we're just going to quote the result here without proof. The amount of potential energy, which is related to the amount of work done in moving the charged particle from here to a long, long way away, is given by this expression here. There's our familiar electrostatic constant. There's the two charges. Notice that it's over r and not over r squared like the force is. Let's use that to do a problem. So here we've got a 75 microcoulomb. It's 3 centimeters away from a fixed plus 120. And then we're going to move it a long, long, long way, all the way out to infinity. I'm not sure why the smart software is taking my micros and making them into capital M's, but those are all micros. Okay, so here, energy at the beginning, when it's close, plus the work done by non-conservative forces equals the energy at the end. Here it is way out at infinity, and here it is close by. Now there is work being done because we're moving this charge. They attract each other, so we're going to have to push on it. There will be a force exerted on it, so there is work. Energy in close here is potential energy. We're doing work, and then we're ending up here way out at infinity with potential energy again. Now we calculate potential energy, as we just saw, using KQQ over R. However, because the final distance is infinity, that's just 0. Because dividing by something really, really big is something really, really small. So we can calculate the work as follows. Now, I'm going to need a lot more room to start substituting this in, so let's move that way over here. Because K is 9 times 10 to the power 9. Now, one of these charges was 120 microcoulombs, and I'll drop the units. Then the other charge is a negative 75 microcoulomb. And then the separation distance was 0.03 meters. And so this number here is negative 2,700 joules. And so we can see that we have done 2,700 joules of work to separate those charges. Now you notice that unlike force, potential energy can be positive or negative. And as a result, we include the polarity, positive or negative, of the charge value in that calculation. So now let's look at like charges. Let's imagine that they're initially separated by an infinite distance, and then we push this one in, this 2.5 millicoulomb in. So energy at the beginning, which is out at infinity, plus work equals energy at the end when they are close. Now, as we saw before, the potential energy at infinite separation is just 0. So the work that was done here in pushing these like charges together is KQQ over R. Since these are like charges, and I'll point out that they're millicoulombs, which is 10 to the power minus 3, since they are like charges, be they like positive or like negative, the potential energy will be a positive number, simply because negative times negative is also positive. So with a final separation distance of 5 meters, we find that our final potential energy and the work done was 7880 joules. So there's a couple examples involving the calculation of work and electrostatic potential energy. We'll do another one or two like that in class. Now, a related concept is the concept of electrostatic potential, or commonly known as voltage. In order to understand voltage, we're going to remind ourselves of something that we've already encountered, which is the electric field. So here's a 2 microcoulomb charge. Over here, we're 75 centimeters away, and we just want to calculate the electric field there. Well, the electric field is given by the ratio of force to charge, kq over r squared. For a 2 microcoulomb, if we are 75 centimeters away, we find that our field strength is 32,000 newtons for every coulomb. And the direction, if you put a small positive test charge there, the electric field, it would be repelled by the 2 microcoulombs, so the electric field is to the right. So the direction of that field is this way, because electric field is a vector. Now, what would be the force if we put a 1 coulomb at that place? Well, this is 32,000 newtons for every coulomb, so with 1 coulomb, we would expect 32,000 newtons on 1 coulomb. Now, 1 coulomb is an astronomical amount of charge. What if we put 1 millicoulomb? Well, that's 1/1000th of a coulomb, so we would expect only 32 newtons, because there's 32,000 newtons for every coulomb. If we had 2 millicoulombs, twice as much, we would expect a force of 64 newtons. So what we see then is that electric field is the ratio of force per charge. It's the amount of force you'd have, the amount of newtons you'd have, if you put a coulomb at that point. The reason we go through this is that electric potential, or voltage, is similar. So electric field is the newtons per coulomb. For energy, we're going to define an energy field, the joules of energy per coulomb placed at that point. And so that's a ratio of potential energy over charge. It has units of joules per coulomb, and we define that as being a volt. Now, we already know how to calculate potential energy. It's kq little q over r. So if we divide that by q, then clearly the q's just cancel out. And so we get an expression for our energy field of kq over r. So let's go back to that example. Now, we said that electric field, remember, was a force field. It tells you how much force you get if you put a coulomb there. We're saying that voltage is similar, except it's an energy field. It tells you how much energy you have if you put a coulomb there. So here we've got our 2 microcoulomb, kq over r. It's the same one as before, the previous example. So it's still 2 microcoulombs, and we're still the same 75 centimeter distance away. Now this energy field is 24,000 joules per every coulomb, or volts. And what does that mean? Well, if you were to put a coulomb there, if you put 1 coulomb at that field point, your potential energy is 24,000 joules. That's what this ratio tells us. If you put a millicoulomb there, at that field point dot, then your potential energy is 24 joules. If you put 2 millicoulombs there, so 2 1,000ths of a coulomb at that field point, then your energy is 48 joules. So what does voltage tell you? It tells you it's an energy field. It tells you how much energy you'll have if you put a coulomb at that point, even if there isn't anything there. This is just an empty point in space. So to recap then, voltage is the ratio of energy per charge in joule per coulomb or volt units, and we can find it for a point charge using kq over r. The potential energy is given by kqq over r. We could also cross-multiply this expression. If you happen to know the voltage and you're putting a charge Q at that point, you could find the potential energy using this relationship here.